Hello students, in previous lecture we have studied interior point concept and important result related with interior point. Like a subset A of metric space, XD is open if and only if A interior is equal to A. A interior is the largest open subset of X containing A, etc. Okay. Today we'll see one more important result about the interior points and then we'll go to the closed sets. So our topic is interior points and closed sets. Points, closed sets. So take the next theorem about interior point. Let XD be metric space. XD be a metric space and A subset of B. AB are subsets of X. Then first A subset of B implies A interior is subset of B interior. Second, A intersection B interior is equal to A interior intersection B interior. Third, A interior intersection B interior is subset of A interior A union. A interior union B interior is equal to A union B interior. So we'll prove one by one. So first, let A belongs to, suppose A is subset of B in XD. What is your claim? A interior is subset of B interior. Okay. So let X belongs to A interior. Then there exists R greater than 0 such that SRX is contained in A. This implies SRX must be subset of B since A is subset of B. This is given. Therefore, X belongs to B interior. Okay. For any X belongs to A interior, since X is arbitrary, and therefore A interior is subset of B interior. Secondly, we have to show that A interior of intersection of two sets is equal to intersection of their interiors. Okay. To show A intersection B interior is equal to A interior intersection B interior. So let X belongs to A intersection B interior. Then there exists some R greater than 0 such that SRX is contained in A intersection B. This implies SRX is subset of A and SRX is also subset of B by definition of intersection. Therefore, this implies X belongs to A interior and X also belongs to B interior. This implies X belongs to A interior intersection B interior or any X belongs to A intersection B interior. And therefore, A intersection B whole interior is subset of A interior intersection B interior. Okay. 1. Now, let X belongs to A interior intersection B interior. This implies X belongs to A interior and X also belongs to B interior. Implies there exists R1, R2 greater than 0 such that SR1X is contained in A and SR2X is contained in B. Take R is equal to minimum of R1, R2 greater than 0. Then SRX is subset of SR1X contained in A and SRX is subset of SR2X is contained in B. This implies SRX is subset of A intersection B. Okay, and therefore X belongs to A intersection B whole interior. And there is no any restriction on choice of X. Therefore, for any X belongs to A interior intersection B interior. And therefore, A interior intersection B interior is subset of A intersection B whole interior. So from 1 and 2, result hold. From 1 and 2, A intersection B whole interior is same as A interior intersection B interior. Is it clear? Now, thirdly, what is our third to show A interior union B interior is subset of A union B interior. So let X belongs to A interior union B interior. Then X belongs to A interior or X belongs to B interior. Implies there exists some R greater than 0 such that SRX is subset of A or SRX is subset of B. Implies SRX is subset of A union B. So for given X belongs to A interior union B interior, SRX is subset of this. Therefore, X belongs to A union B interior, and for any X belongs to A interior union B interior. This implies A interior union B interior is subset of A union B interior. So note, for Q and Q complement in RU, Q interior is equal to Q complement interior is phi. Set of rational number. Its interior must be phi. Since if I take any rational number and any open sphere about rational number, it is interval. It is interval. Okay. Since for any X belongs to Q, open sphere about X is X minus R to X plus R is not subset of Q. Okay. So every point of Q is not interior point. Okay. Q complement. Q complement. Right. And therefore, we'll get this. Now, this implies Q interior union Q complement interior is equal to phi 1. Now, Q union Q complement interior is equal to R interior is equal to R, since R is open in RU. So from 1 and 2, Q interior union Q complement interior is proper subset of Q union Q complement its interior. So equality doesn't hold for union. Equality doesn't hold for union for interior concept. Now we'll go study concept of closed sets. Closed sets. A subset of metric space, a subset say F of metric space XD is closed if and only if F complement is equal to X minus F is open in X. Every definition is always if and only if condition, remember it. Okay. So subset of metric space is closed if and only if its complement is open. Its complement is open. Example, in RU. Okay. Closed interval AB complement is nothing but minus infinity to A union B to infinity. Is union of two open intervals and hence open set. Two open intervals and hence open set. And hence open set. Implies closed interval AB is closed in RU. Is closed in RU. If I take, let A is equal to say A1, A2 dot dot up to AN be finite subset of R, finite subset of R where A1 less than A2 less than dot dot up to AN. Then A complement. What is your A complement? Is nothing but minus infinity to A1 union A1 to A2 union A2 to A3 dot dot up to union AN minus 1 to AN union AN to infinity. Is union of open intervals, is union of open intervals, is union of open intervals and hence A complement is open set in RU. Therefore, any finite set A, any finite set subset of RU is closed. In fact, every finite subset of any metric space is always closed. Every finite subset of any metric space is always closed. We'll also prove it. We'll also prove it. Next, similarly, third, similarly, set of natural numbers, set of whole numbers, set of integers, okay, Cantor set are closed sets in RU. Now natural number 1, 2, 3 and so on. What is n complement? N complement is nothing but union of n to n plus 1, n is equal to 1 to infinity. Open interval 1 to union, open interval 2, 3 union, so on. Open interval 2, 3. Is open. If I take say Z complement, okay, Z complement, I'll take it as Union of n is equal to minus infinity to infinity, open interval, n to n plus 1. Again, minus infinity to infinity is open. Okay. So if I take minus 3 plus 1, that is 2. Okay. If I take here n equal to minus 1, then this is 0, minus 1 to 0, that is open interval. So, right. Similarly, W is also open. Similarly, W is also open. Cantor set. I have not explained what is Cantor set. So in one lecture, I'll describe what is a Cantor set. Then we'll prove that how it is closed, how it is uncountable, etc. Okay, so I'll require one complete lecture for explaining Cantor set in detail. That is a very important set in analysis, Cantor set. Okay, fourth one, set of rational number q complement are not open. Are not open in RU implies this q complement its complement is equal to q are not closed in RU. Why this set of rational number is not open? Because if I take any neighborhood, any open sphere about rational number, it is interval, and that interval contains rational as well as irrational numbers. So it is not subset of q, not subset of q complement, and therefore set of rational numbers, set of irrational numbers are not open as well as closed sets. Open as well as closed set. But if I take finite set containing only rational numbers, then it becomes a closed set. Every finite subset of any metric space is closed. Is it clear? Now we'll prove one important result about the closed set. Okay. So theorem. So first we will define the closed sphere. We will define open sphere. Okay. So let XD be metric space. Then for x belongs to x and r greater than 0, the set SR close bracket x is set of y belongs to x such that d of yx less equal r is called as closed sphere. Closed sphere centered at x with radius r. With radius r. So we'll prove that in any metric space, XD, every closed sphere is closed set. Is closed set. So for x belongs to x and r greater than 0, let SRx is equal to y belongs to x such that d of yx less equal r be closed sphere in x. What is our claim? SRx is closed set. That is to show its complement, SRx its complement is open in x. So I have some say this is my x, this is my say x r, this is your s r x closed sphere. I have to show that its complement is open. So we'll take some point y here, y from that. Okay. So let y belongs to SRX, its complement. This implies d of yx is greater than r. D of yx is greater than r. Take r1 is equal to, take 0 less than r1 is equal to r minus d of yx 1. This is my r1. Okay. Then to show SR1 y is subset of SR1x, its complement. Its complement. So we'll take arbitrary point z from it. We'll take some arbitrary point from z. So let z belongs to SR1y. Then d of zy is greater than r1 is equal to r minus d of yx. Is it clear? D of zy is less than r1, is less than r1. Is it clear? Now by triangle inequality, d of xy is less equal d of xz plus d of zy. Is it clear? This implies d of xz is greater equal, d of xz is greater equal d of xy minus d of zy. Is it clear? So this is strictly greater than d of xy minus r1. Why? Since d of zy is less than r1, so multiplying both sides by minus sign, we'll get this. So d of xz is greater than d of xy minus that. What this implies is z doesn't belongs to, this z doesn't belongs to SRX, because distance with this d of xy minus r1 is equal to r from 1. Okay, and therefore z belongs to SRX its complement for any z belongs to SR1Y, SR1Y. This implies SR1Y is subset of SRX, its complement. Thus for every y belongs to SRX is complement, there exists R1 greater than 0 such that SR1Y is contained in SRX, its complement, and therefore SR1, SRX, its complement is open, and therefore SRX is closed set. Therefore SRX is closed set. Okay, so here we proved closed sphere is a closed. Closed sphere is closed. So example of closed sphere in RU, SR1, SR2 or SR1, this will become 2 minus 1 to 2 plus 1, which is equal to 1, 3. Close interval. Like this, okay? Second, in XD, discrete metric space, XD, SRX, this is singleton X for every R less than 1, and SRX is whole set X if X greater equal 1. X greater equal 1. Okay. So note S1 X is singleton X and S1 X is whole set X in discrete metric space XD. So after open sphere there is concept of closed sphere, but at the time I forget to explain closed sphere. So while showing every closed sphere is closed set, I have also constructed or given examples of closed spheres. So for open sets we have proved that in any metric space X, empty set and whole set are open, arbitrary union of open sets is open, finite intersection of open sets is open. Here also we are going to prove that in any metric space XD, empty set and X are closed set. Secondly, finite intersection of closed sets is closed, and finite intersection of closed sets is closed. Okay, and arbitrary union of open sets is open. So arbitrary intersection of closed sets is closed, and finite intersection of open sets is closed sets is closed. We are going to prove these results in next lecture. So with this discussion, today we'll stop here. Thank you. Bye bye.